In this particular video, we're going to study the bootstrap technique, or not the whole technique, just creating bootstrap samples for a specific line of business. Actually, it turns out to be workers' comp. So let me go to it. And first of all, what I'm going to do is find a good model for a good probabilistic trend family model for this data. I'm in the wrong part of my, let me go to Bootstrap part of my database, and I'll go to triangle group ABC BS. I'll generate, well, I can use a wizard to create a good model, but I've already, well, why don't we do that? That's good fun anyway. So let's create. So what's the structure in this data? The structure in this data is that when you look along the calendar years, there are major shift in trends. So there's, let's open the residuals also. Remember, residuals represent trend in data minus trend estimated by the method. And with PTF modeling framework, with any model in the PTF modeling framework, we have a succinct picture of what is estimated by the method. We've got descriptors. So for instance, the method along these calendar years estimates 6.52% plus minus, between 84 and 85, 10.83%, and thereafter 16.91. Now, some would argue, well, there might be a trend change here and a trend change there when you look at the residuals, because they don't seem to be around zero. If you estimate that and optimize, you'll find out that there's nothing there. Now, if I set the trend to zero along the calendar years, now the trend in the method is zero. So you're looking again, the trend in the data minus the trend in the method. Well, you can see that here, that you're overfitting all the data, and over here there's a huge trend, okay? So that you know that the trend in the method has nothing to do, which is zero in this case, has nothing to do with the trend in the data. The trends in the data are very different to the trends estimated by the method. If we now run the previous model that captures those trends, I'll just run it from here. Now we are saying that what's left over in the residuals is a trend of zero. The trend in the data minus the trend in the method is zero, and this is then that the fact that we know what the trend in the method is, we therefore know what the trends in the data are. So if we instead apply the MAC method to the cumulative data, why don't we do that? That's the residuals we get. And let's compare the two sets. Okay. So the MAC method cannot capture these calendar year trends. Okay, cannot capture these calendar year trends. The MAC method has captured some of the trends. We don't know what they are. The MAC method, we might show, we will show, in fact, does capture some of the calendar year trends, but we don't know what they are. All we know really is that the difference between the two is not zero. The difference between the trend captured by the MAC method and the trend in the data is not zero. If we now, I just want to write something down, so let me pause. If we now compare the two modeling frameworks, if in the PTF modeling framework, in this particular model, I set the trend to zero, you notice that the residuals look a bit alike. On the right side, I've set the trend in the method to be zero, and you can see that you've got an increase in trend here. On the left side, we just estimated the MAC method with an increase, but we don't have any control on the parameters here because we don't have any parameters. In the MAC method, on the extended link ratio family, we don't have any calendar year parameters. On the right side, we do. So let's re-estimate the model again so we can capture those trends. With the MAC method, we can't capture those trends. Some might argue, why don't we just use the MAC method to the last 4 years? 3 years. Well, there's still a trend. And even if the MAC method estimated that trend, you wouldn't know what it is. Okay. Why don't we now, what I'll do is now I'm going to simulate bootstrap triangles from this method. Now, there's a problem here. You can see that the residuals are not random around 0. Now, for the bootstrap technique to work and actually give you the variational in the data, the variation in the real data, the residuals should all, standardized residuals should all come from one distribution. We discussed that in chapter 9.1. So what you're going to be doing really when you use the bootstrap, you're going to take these residuals which are highly positive and you're going to put them in other parts of the triangle to create new fitted values. These residuals that are mostly negative, you're going to put those and mix them in some other part of the triangle, say this calendar year, and put them there. So as you start mixing these residuals, you'll find out that the bootstrap sample from this method doesn't look anything like the real data. Okay? And that's because the method does not capture the features in the data. So let's create 3 bootstrap samples. And here they are. Okay, and we'll copy the MAC model or the MAC method to each one of them, which is really the default model, but anyway, it's a quick way of me running the MAC method for each one of these data sets. So now for the 3 bootstrap samples, get rid of PTF here. So let's look at, this is the real data, that's a bootstrap sample, that's a bootstrap sample, that's a bootstrap sample. So can you see that the trend structure, MAC applied to the real data, is kind of being covered out, it's kind of being masked because you're mixing positive residuals with negative residuals in fact creating the bootstrap samples. Okay, so you've lost the structure in the real data in the bootstrap samples from the MAC method. If instead I go to my model, probabilistic trend family model, this model, which captures the trend structure along the calendar years and also the trend structure along the accident years and development years, why don't we just for the moment create 1 bootstrap sample, only 1. I'll go back to the triangle group, and it's PBS. I'll go to the triangles, PBS, and I'll accumulate this data. So I'll call it, it's from model called good. Well, that's the incremental model. This is this model. I've called this model good. You can see that in the title here, good. Okay, let's go to data sets. Make sure I use the same exposure here. And let's now apply MAC to this particular triangle, but this is really a bootstrap that was created from the PTF good model. Let's look at that. Let's use the LOF. Let's look at the residuals. And now let's do a comparison. Well, you can see now, these two here are very highly related. They are the same, they have the same features. These 3 were created for MAC. Okay, they were created for MAC. The MAC method applied to the real data. This is the MAC method applied to the real data. This is the MAC method applied to a bootstrap sample that came from the model, the good model, this model, for the incremental data. So by a quick summary here, the PTF model creates bootstrap samples that have the same features as the real data incrementally, I'll show you in a moment, and the real data cumulatively. Okay? The cumulative real data and the incremental real data, whereas the MAC method creates cumulative bootstraps of the cumulative data that bears no resemblance to the real data. If I now go back to the triangle group, and why don't I now go back to PTF and first of all simulate another 2 bootstrap samples from PTF. So now we have 3 in here. And to each one, I copy the good model. And now I run it. Do we have the real data? What happened to the real data? We've got the real BS, BS1, BS2. Okay, we've got 4 now. Okay, which is the real data? It's very hard to tell. This is the real data. This is a bootstrap sample from model called good. So is this. So is that. If I now look at one parameter in each direction for each one of these samples, 3 are bootstrap, 1 is the real data, and compare them, it's very hard to tell which is the real data. Agree? So bootstrap samples from the optimal PTF model has the same features, the same trend structure, and the same features as the real data incrementally and the real data cumulatively. Let's now take one of the bootstrap samples we created from MAC and create its corresponding incrementals. So let's take this one came from MAC, it's cumulative, and create the corresponding incremental one. So it's from BS, and we'll call it from MAC method. And now let's go to data sets, MAC. It's incremental. Let's put in the base exposure. Let's now copy the model to it. Let's run it. You can see you've got all the parameters that are insignificant. Let's open its residuals, all the residuals. Let's run the starting model on each one parameter in each direction. Okay. Which one is the odd man out? Let's try and find out. Well, that one is the odd man out. And that's a bootstrap from MAC. If I now estimate this model to each data set that shows you major calendar year shifts, it'll be very easy to tell which comes from MAC. So the real data has major calendar year shifts. This is called a statistical chain letter model that removes development year trends and accident year trends to see what's left over along the calendar years. In the MAC Bootstrap, there's hardly anything left over along the calendar years. This is Bootstrap from PTF, real data, Bootstrap from PDF, Bootstrap from PDF. Can't tell the difference. Okay, so for triangle group ABC, which is really workers' comp, the MAC method can't capture the calendar year trends. The bootstrap samples from the MAC method bear no resemblance to the real data. So any subsequent calculations based on bootstrap samples for calculating standard deviations, means, or anything else you like, it's got nothing to do with the real data. Yet bootstrap samples from the optimal PTF model are replications of the features in the real data. And any calculations based on those samples, which is quite interesting, any calculation based on those samples, if you did many of them, would be the same answers if you were using the parametric model that you've tested. In other words, the model for the real data is that one, it's model good. If you assume this model, with normal distributions, with this particular variance, very small variance, this data's got very little process variability, you would get the same answers. In other words, you could drive the mathematics because you know the difference, the relationship between normal, multivariate normal on a log scale and the corresponding log normal on a dollar scale, because you know all that. If you were doing bootstrapping to find the distribution of the aggregate reserves, you'd get the same answers if you were using the mathematics. Everything works through the mathematics. So there's no need here to do any bootstrapping. The only reason we did it is to show you that bootstraps based on the optimal PDF model, I guess I'm repeating myself, represent the real features in the data, yet based on math data. Thank you.